Welcome to Everything Distributed. Today, we are going to check a real system, which is Cassandra. And the talk today is based on three of the readings. The first one is by the original Facebook paper on describing the design and implementation of a Cassandra. And then the second one is by Amazon talking about like what is NoSQL. And then the third one is that the originally Cassandra is inspired by the design of Dynamo, which was designed by Amazon. And the third one, this article, is the reflection of Amazon's CTO after they have used Dynamo for a decade. So the overview, what is Cassandra? Cassandra is a distributed storage, and the particular type of storage is called NoSQL. So originally for database, we have this very popular paradigm called SQL database. And then like nowadays, we have a large scale like distributed system and geo replication. So like people thought that okay, actually we need a new kind of storage paradigm, and then they have something called not only SQL, so it's NoSQL storage, and then there are lots of debate whether we really need NoSQL, but like that's not the focus today. And then the second one is that even for NoSQL, there are lots of different kind of NoSQL database. The reason is that each of them kind of want to find a sweet spot. And for Cassandra, the particular data structure is called wide column storage. And then to understand that, we will need to go into detail how they partition the data, how do they store and process data, how do they query the data. But again, that's not a focus today. So right now, just remember that it's NoSQL and wide column storage. And originally, Cassandra was designed to run inside a data center, but like right now, people also extended it to geo-replication, so you can do like this multi-data center thing. Originally, it was used heavily by Facebook, designed by Facebook, and then later it's open source, and now it's an Apache project. And right now, as far as I know, there's a one company that's like there's a main contributor which is called Data Stacks. And why do we care about Cassandra? And the reason is that lots of big tech company and lots of kind of big company are actually using Cassandra in some way. And then at least according to their website, it's that Cassandra is used by 40% of the Fortune 100 company. And from my experience, because I also did research, I kind of hacked Cassandra, and my student report to me that actually they because they have this experience in Cassandra, and when they go to interview, employer, the company, like the interviewer, ask them about their experience. So that's something good to know. So like for Cassandra, when they design this, why do they want a new system? The first one is scalability and availability. So like what they want is that they don't want to have a single point of failure. So they don't want to have a leader-based design. Instead, they want to have leaderless. And because if you remember the cat theorem, we cannot have everything. So they sacrifice consistency. So originally for Dynamo and Cassandra, they were designed for eventual consistency. But of course, right now they figure that eventual consistency actually is not general enough and it's very difficult to deal with. So now they are starting to add back the support to stronger notion of consistency. And then for the scalability, if you remember from the very beginning, they want to have this scale out property, meaning that once you add more machine, you should have a linear increase in performance, especially we care more about throughput here. And then they use like current replication to replicate their data to achieve scalability and availability. And then one cool thing about this is that there are several knobs that you need to tune. You need to decide that how to replicate, how to query your data, so that you can find a sweet spot in the trade-off between consistency, durability, and latency. And finally, they want to design it to be very easy to manage. So that's all very cool. And but because they want to achieve all those very good goals, then Cassandra itself actually is pretty complicated. So here is a very rough structure or architecture of their components. The underlying thing is a message layer. They need to know how to send message. They need to do their own serialization and deserialization. And then on top of that, they also have some compaction manager. They want to compress the data. They want then kind of to save the storage, to save the bandwidth. And then there's also failure detector that we are going to talk about next later. And then here, partitioner, something we know, then how you decide the partition, how you have the shard of your data. And then my favorite part is a replicator, where we do the replication, where we need to satisfy certain consistency. It's here. And then right now they also add a support for consensus in particular pixels. It's also implemented in this layer. And then of course they also have a storage layer. That's all the logic for your database engine, where you process your query, where you decide how to store your data into your memory, when do you persist your data into a disk. And then these two are kind of user-facing one, so that they have this kind of CQL, Cassandra Q query language, that you can use to kind of read and write the data, or even do this transaction. And then they also have their stress test tool there. And today we are actually only going focus to on this replicator one. And then the reason that I color this blue thing, because that in my research we hack this two layer a lot, and then that's very interesting to check. So partitioner, remember, why do we want to have partition? Why do we want to have sharding? It's because we want to have scalability. We don't need all the server to have the same set of data, because if we partition, if we have many sharding, then if a query that touch only one particular part of the data, then it's very scalable. But the way you do partition is that you need to know where your key value pair is stored. So right now, even though Cassandra is designed as a column storage, but for simplicity, let's assume that it's a key value pair. So given a key, you need to find where the data is stored. And then the Cassandra use the techniques called consistent hashing. You can think of that as a particular way of doing hashing, so that it's easier to do load balancing, and it's easier to manage data when some server fail or new server come in. And then another way, another technical term is that this thing is called distributed hash table. And then when you use distributed hash table to find the data you want, that's called routing. And I want Cassandra particularly use the notion of one hop, DHT, and then you don't really need to do the routing, because every server actually know the data stored at all the other replica. But you still need to know the mapping. And then this mapping is through consistent hashing, and then it's implemented inside in this partitioner layer. So if you remember what is partitioning or what is hashing, it's like given key, you need to find a server who has the data, and then that's through a call through using a hash function. And then they provide several strategy of doing their partitioning or doing their sharding, and then basically this strategy decide how your data is located or distributed across the nodes inside the same data center. And then here I just screenshotted. There's a different way of doing hash value, and then based on your workload, you want to select the strategy that fits your need. Okay. And then this just a recap from the partitioning lecture. The idea is that you have key, and then once you hash it, then it will map to the server. And then I remember partitioning and replication, they are two different things. So right now, since we only care about partitioning, then each server will have a different set of data. Okay. So what you do is that you have a predetermined hash function, and then you hash the key k, and then this will give you some number. Suppose it's 10, then you just check that which server has 10. So suppose that it's a store 1 to 10, this guy is store 11 to 20, so on and so forth. So after you run this hash function, you will know that, okay, the red server actually have the data I need. Then you will go query this server or this replica. Okay, so that's how you use partitioner. And then different strategy basically use a different hash function. Okay. Then the next one is a replicator. So remember, we want to have replication because we want to make sure the data is durable, meaning that if one server dies, you still can access the data. And we also want availability because that if some server is slow or if your network's partition, you still want to be able to query some server to get your data. And then the way to do that is is to use replication. But in terms of this partitioning and replication, how do we use them? And then in Cassandra, actually, it's a slightly more complicated than what we have learned so far. And the simple strategy is the simplest one. It's very similar to what we have learned. It basically doesn't really care about what underlying network looks like. And then a slightly more fancy one is that you have a network topology strategy. So actually, it really cares about like where the data, where the replica is located. You also care about like where you are using like multiple data center to do the replication. And so now let's look and focus on the case of one data center. And suppose we only have 4 servers, just like how we do the sharding before. We have red server, blue server, orange server, and purple server. And each of them handles a particular set of data based on the partitioner we use. And remember that like when we use replication, suppose our replication factor is 3, so that each set of data we want to copy exactly 3 times. And then let's assume that we use simple strategy. So the way it does is that first, the data, this is the server picked by a partitioner. So of course, this server has a red set of data. And then if I want to replicate 3 times, that means that I need to find 2 more servers to store the red set of data. And then simple strategy is very simple. You have a logical ring here. And what you do is I find the next guy in the clockwise direction. So this blue server also need to have red data, and orange server also need to have red data. And then we also apply the same knowledge in the blue server, blue data, and also orange data and purple data. So in this case, actually that each server needs to have 3 set of data. And so in this case, that replication factor is 3. That's why that each color we only have 3 times. But like in practice, that the ring will be much larger, maybe 10 servers or 20 server. Okay, so that's how we do partition and replication at the same time. Then the next one is that all this circle I draw, it's all the server I mentioned, it's actually the virtual one. But like how do we map to the real physical machine? And then Cassandra has this idea called snitch. So what snitch does is that basically you need to tell snitch what your network topology looks like, how your server is connected, where is your kind of switch, router, load thing. So it will automatically figure out that how to route the message, how to send the message. And then it also allow the Cassandra to pick that where to place those virtual nodes so that it can avoid correlative failures. So if you will, or you are dealing with a real data center or real cluster, you will know that correlative failure is actually the thing, because if a rack or if a switch just dies, then all of the servers that you cannot access them. Okay, so like Cassandra has a way to address this challenge. Okay, now let's look in more details for the replication. How do we do a write and how do we do a read? And then there are two goals, is that it should be lock-free, meaning that I don't want to use any kind of consensus. I don't want to use atomic commit. I want it to be there's non-blocking, and then it's fast. Okay, and then it start with client, and client will send a write to one coordinate node. So here, the cool thing about Cassandra is that if you remember, one goal is that it doesn't want to have a single point of failure. So the way it does is that, again, we have 4 servers, and then we have this client. Then client can actually contact any nodes to be the coordinator. And then again, for coordinator, there are many choice on how to select it. And then it's actually very flexible. You can pick it per key, per client, or per query. And then that's a different policy that you can check. Okay. And okay, actually, let me clear those. So let me remind you again, like for Dynamo style or like for leaderless replication, how do we do it right? The way we do it is that here we have a client, and then let's say that we have like 3 replicas, and then we have a coordinator. So actually coordinator, it may or may not have the data that this client needs. So this is coordinator, this is client. So the first thing client is I go to coordinator, and then I say, hey, I'm going to issue this write request W, and coordinator will forward the write to all the replicas. Say W, W, W. And then replica, upon receiving, you will check whether I want to apply this write request by checking the timestamp. If like this write request is that the newer contains a newer version, then you will write it into the memory. And once it write to memory, or like sometimes if you configure it to be write to the disk, it will return an egg. And then here, the client can configure the system to specify the size of a write quorum. So suppose the size of write quorum is 2 in this case, then coordinator receive 2 acknowledgement. It will tell the client say that, hey, your write is complete. It's good to go. Even though this write replica has not returned an egg yet. Okay. So that's how they do the write operation. And then the practical system is actually slightly more complicated. Remember, they want to achieve this high availability and then kind of always available notion. And then like Cassandra is actually claimed to be like write optimized. So they want to make sure that write can always be complete. So that's what they say is always writable. And then they invented a mechanism called hinted handoff. What that means is that even though the coordinator for the write, but like it's possible that all this replica is somehow very slow. So that if this write quorum the client can actually configure it to be 0. In that case, the coordinator can immediately send it back to the client, say that, hey, it's done. You know what? I will make sure that these 3 replica will write your data later. And then this may be like stored at the coordinator for several hours, but like this okay. And then they do that because they want to have a high performance of a write. Okay. And then the other thing that we haven't touched about is that across data center, how do we do this kind of replication? And then the way to think about the Cassandra is that you should always think about you have a virtual ring. Here is one data center, and then here's another data center. Then for each data center, you also have a coordinator. So like coordinator, suppose this is the coordinator at data center 1, this is coordinator at data center 2. And then when you do replication, even though your data may be stored on like these 3 replicas marked by the cross, but like this coordinator should always go to the coordinator at the data center 2, and then coordinator will do the write for you. Okay. And then for this purpose, this is that because that sometimes for cross data center, the communication is very expensive. So you don't want to send too many messages across data centers. And then the other thing is that this rings, the servers or replica may come and go, they may change. So that for this coordinator at data center 1, you might not know who has the most recent data. So one usual way to do this is that we have a coordinator or the notional leader that's in charge for all the write and read inside this data center. And then the way they do election is to use Zookeeper, which is an open source kind of consensus or leader election protocol that's very popular. Okay, so that's that. Then now let's talk about read. And read is actually very similar to what we do, what we show for the write. So again, we have a coordinator and then we have client. Then client will contact the coordinator will figure out who are the replicas, coordinator will forward the read request to all the replica, then all the replica will return it with some data. And then again, you can specify the size of your read quorum. So suppose in this case, a read quorum is 1, then the coordinator that once it gets this D, it will directly forward D to the client. Then the client will do that. The client will return the data D. And something slightly different. Oh, actually, in this case, this should be 3. So what I talk about here is the way that usual leaderless replication protocol does. But like for Cassandra, they said that for performance issue, actually they don't really do that. What they do is that first, let's specify this R. So what's the meaning of R? The meaning is that the number of replica you need to contact. So actually they don't send the request to all the replica. They just send it to 3. And then here, how do you pick 3? Usually that you have a list of the replicas that have responded quickest in the past. And then in this case, actually that the coordinator need to wait for all of them to return the data. And then it will compare which one has the most recent data by comparing the timestamp. And then suppose this guy, this D is the most recent one, then coordinator will forward this back to the client. And then this completes the whole read protocol. Okay. And then one cool thing about this is called Rerepair. So the way to do to think about this is that remember this RQ thing, but like the number of replica actually is larger. So it's possible that you also have other replica that has the data that you are querying. So what the coordinator does is that not just on the critical path, but like when it's kind of free, it will also send the data to the other replicas. And then this replica will send the data back to the coordinator. And then the coordinator will need to check that, do this consistency thing. They will need to check that suppose this is replica 1, replica 2, whether those two replica have the most recent version of the data. If they do, that's good. You don't need to do anything. But if they are older, then the coordinator needs to do this thing called repair, meaning that it needs to forward D again to the replica 1, replica 2 to help them catch up with a new value. And then that's how they achieve eventual consistency. Is that suppose the network is stable, and then if there's no more right operations, then eventually every replica can learn the most recent value by this mechanism of a repair. Okay. And then the final technical thing I want to talk about is this membership and then failure detector thing. And then if you remember on how we do the read and write, we have this ring, and then we have the client needs to know like who should I contact, and then once you become a coordinator, because that client may contact anyone, the coordinator needs to figure out who has which set of data. So not only is the coordinator needs to know the partitioner strategy, they also need to know a list of live server, because some server might be slow, some server might crash. So they need a way to figure out who's alive. And then the way to do that is that the notion of failure detector. So very high level, how they do that is the servers replica, they will exchange message. Usually you call that heartbeat message. So it's kind of every now and then I tell you, hey, I'm alive. And then if I haven't heard you from too long, then it's possible that you have crashed. And of course, in practice, it's much more complicated than that, because that message might be delayed, or a message might be lost, or there might be false positive, false negative. So like Cassandra, what they implement is the mechanism called accrual failure detector. So it actually measures the probability of a server a probability distribution to estimate the server failure. And then here's the paper. It's a very good read. I encourage you to read the paper. Okay, so that's a membership and failure detector. Basically, let the coordinator know who's alive, who has died, so that it can query the data that it needs. And then if you are interested in all this detail, I encourage you to read in more detail about like on the critical path, how does Cassandra, how does the coordinator does the read, how does it do the write. It's a very cool thing to see how they design a system. And then there are many other things that I haven't touched. For example, like in the kind of kernel, how they do this database engine, how do they write the data into commit log, what is the structure of the memory, why can they support a very efficient write, and then how do they index the data, and then how do they find the data, and how do they do compaction, and then for the read, how do they fetch the data efficiently, and why is the read slower than write. Then yeah, there are tons of many interesting things, but like it's kind of beyond the materials that I plan to cover in this lecture. Okay. So that's all I want to cover today. And then the takeaway is Cassandra. and many on the architecture. How do they do replication? Why do we have a partition, and how to combine partition and replication together? And then there are many other things that I haven't touched, but hopefully I give you some insights on the beauty of distributed computing. So you kind of know the theory of those things, and then once you have a certain understanding, then you can go back to check how real world system is implemented. And then once you have this knowledge, you can be more comfortable of using the system. So all those are different tuning, different knob, and then different strategy. You have some sense of like how to use them. And then even if you are not going to build your own distributed storage, your database, but that some knowledge in distributed computing actually will make you a better application developer if you want to use Cassandra or something similar. And then that's why I encourage you to know more about distributed computing. You should, it will be very useful. Okay, so that's all today. Thank you.